Thank you. So for appetizers today, we have some DPAPI, or like Jim Rush likes to call it, DPAPI. Just a quick word about me. My name is Claudio Contin. I work as a principal consultant at Tier 0 Security. I actually have a background as a software developer. I've been a developer for about 12 years, done a bit of sysadmin as well. Now I mainly do offensive security, so I work as a pen tester, red teamer, purple teamer, and I also run training. When I don't work on computers, I enjoy skiing and surfing, or at least I dream about it. So why do we need to care about the DPAPI? So from an offensive security perspective, it can be fairly interesting, especially when you're working with specific scenario, when you're working on client networks. It can be a red teaming, or it can be a kind of a goal-focused kind of internal penetration test on the corporate network, right? If you work as a sysadmin or on the blue team side, I think it's good to understand how the DPI works and the various intricacy of the technical inside of the kind of the Windows system that handle the encryption and decryption using the DPAPI. Also, some things have recently changed around the DPAPI, so this talk will cover a bit of the recent changes that happen in the area as well. So to start off, I'll talk about a story. So I was working on a job probably a couple of years ago. So the scenario was the client was interested for trying to understand if anyone on the corporate network and internal network with valid Active Directory credential was able to obtain access to a secure network. Think about the secure network, it could be like your typical OT network, SCADA network, or so on, right? So only a restricted number of staff members were allowed into these secure networks. So the goal was starting from a low privileged domain user in the corporate, checking if you can gain access to the secure network, right? So talk about the DPI and how the DPAPI helped us achieve the goal in this particular scenario. So when we talk about data protection API, we're talking about really literally is encryption. That's literally all it is. So data protection in this case is purely encryption, okay? So data protection API is the built-in way for Windows to encrypt data. It is actually very, very simple. So the API, when Windows provides you for using the DP API, is extremely, extremely simple. That allows you as a developer not to need to care about implementing your own crypto. You don't need to understand algorithm, encryption algorithm, or anything like that. You purely use API. Windows does the magic for you, and it is fairly secure. So as a developer, how do you actually use the DPAPI? So the DPAPI functionality is provided by the built-in Windows DLL called crypt32DLL. And if you're writing C or C++ code, you need to include the DPAPI.h header. And the two main functions I will focus on for today are the crypt protect data and the crypt unprotect data. So these are really the two main functions for the data protection API. So the crypt protect data, as the name kind of implies, allows you to encrypt data. So you pass your blob of binary data to the function. The function returns a blob of data, which includes the encrypted data, as well as some metadata. We'll talk about soon what this metadata is, okay? And the crypt unprotect data, it accepts the blob of the encrypted data and gives it back the plain text that was originally passed into the original function. If you're writing .NET, you can also use the DPAPI by importing the system security cryptography namespace. And literally the only function you need to know to encrypt data using the DPAPI in .NET is the protect data.protect. So you pass the byte of, in this case, it's text as an input. You pass the entropy, which is not compulsory, so you can specify entropy to add complexity to the encryption. And to unprotect the data, you call literally the protect data to unprotect, pass to the encrypted blob as input. The data protection API also has two other functions called crypt protect memory and crypt unprotect memory. So this is used if you want to actually encrypt data within the process memory. So the data will not get stored on disk anywhere, will literally be in the process memory encrypted. So when the process needs to use the data, you will go and protect memory, use the data, and then re-encrypt it afterwards. The fifth and last function that the DPAPI provides is called crypt update protected state. This is not very relevant usually. It's only used when Active Directory domain is migrated to a new domain. So in case the security identifier of the user changes, this is a way to kind of migrate the data into the new domain. So, okay, so we know how to use the data protection API as a developer legitimately, but how does it work? So to be able to understand it, especially from an offensive security perspective, is we need to understand how it actually works under the hood, right? So of course, when we talk about encryption, there are keys. That's the case for the DPAPI as well. There are keys involved, okay? So the first set of key is called session key. So that's the symmetric key that is actually used to encrypt and decrypt the data. One very important thing to know is that the session key is not actually stored anywhere on the system, okay? Even though it's the actual key used to encrypt and decrypt, the key is not stored anywhere, but it's actually derived from something else. This something else is master keys. So master keys are also referred to as strong keys. These keys are not used directly for encryption. These keys are per account, per different user, and also we'll talk about machine accounts as well, which can also use the DPAPI. These keys are actually stored on the system, on the Wisdom system, and of course they are not stored unencrypted. The only unencrypted version of the data protection API keys of the master keys are within the local security authority subsystem service, or LSS. So if a user is currently logged on to the machine, they are using a software which uses the DPAPI, the master keys will be likely stored in this process unencrypted. Master keys expire. So master keys has an expiry by default of 90 days or 3 months, okay? The reason is if an attacker is able to compromise a master key of a user, they will not be able to obtain and decrypt all the data which might be protected by other master keys that the attacker didn't gain access to, okay? One important thing to know is that the expired master keys are never deleted, okay? They're always kept forever until the host is alive in the user profile directory. So how does encryption and decryption of data protection API works, okay? So we know that the master keys are stored encrypted on disk. Symmetric key is derived by master keys. So in order to decrypt the master keys as an attacker, we need some extra additional data or knowledge. So what is this data? Let's have a look what this data is. So to be a bit more precise is we need to have this data, which will go through a key derivation algorithm, which will be used to decrypt the master keys and then derive the symmetric key. The additional data is very, very dependent on in which context we are talking about. So the additional data is different from local accounts of the machine, so user accounts. Domain user have a different context to decrypt master keys, and machine services have a different way as well. So let's have a look at the various differences, okay? So let's start with local accounts on a single host only, okay? So in this case, in order to decrypt master keys, the DPAPI under the hood, what it does is it creates a SHA-1 or SHA-5112, depending on the operating system version, to pretty much generate a hash based on the user password. Okay, this derived hash is then sent through a password-based key derivation function together with a 16 randomly generated salt and iteration count. I believe the default iteration count is 2000. The result of this goes via an additional function, key derivation function again, and the resulting of this iteration is the actual key which allows you to decrypt the master key, okay? So where the actual master key data is stored on the file system, the default location is under C username, account name, app data, roaming, Microsoft Protect. So for every account, the actual master key data is stored in this particular place. Just to be aware of, if you're trying to use Explorer like the GUI to browse the files, these files are hidden by default. So one way to look at them, you can use command prompt or PowerShell to kind of display hidden files. Another important files related to local accounts user only is the cred_ist file. So what this file is, so these files pretty much keeps history of user credential. So when the user changes their local account password on the machine, the DPAPI hooks into this process, and what it does is it stored the previous clear text password in this cred_ist file using the new password to encrypt the file itself. So the reason it needs to do it is because when it tries to decrypt one of the master keys, if that fails, what the DPAPI does, it goes and tries all the previous user password, okay, which are stored in this particular file called cred_ist. So if we look into the file system, if we look into the user SID, so the user SID is just a unique identifier for every user on the host. So both are the actual master keys, which are stored encrypted. Okay, so if an attacker, I'm able to obtain these master keys. If I'm not operating under the user context, I don't know the user password, this key would be very useless to me. So let's talk about domain user instead. So domain users are a little bit different. So for domain user, I mean Active Directory domain users, okay? So the location of the master key is exactly the same. There is no difference whatsoever. One of the differences is that the cred_ist file does not exist whatsoever for domain users. So in the case of domain user, what happens is when a new master key is generated on one of the hosts, the host itself will go and grab a public key from the domain controller. So the domain controller, the first time the domain is set up, the domain controller will generate a RSA key pair, private and public key. Private will be only stored on domain controllers, of course, will stay there. Whereas the public key will be sent to the various hosts on domain join host on the net. So when a new master key is generated on the host, the key is actually encrypted with the current user password and also is encrypted with the public key of the domain controller. The reason is if the user forgets the credential, the only way for the host to decrypt the master key would be to send the key to the domain controller over a secure channel. The domain controller has its own private key, will be able to decrypt it, send them back to the host to carry on with its own operation. The other difference is that the key is not actually encrypted with the password of the user, but in this case, it with the NTLM hash of the user, which is kind of the hash derived from the password. In terms of local machine, so the system account, which is the high privileges account on Windows, as well as local services like network services and so on, they can also use the DPAPI. So the master keys for the local machine account are stored in this path. So Windows System 32, Microsoft Protect. So these are the master keys of the actual system account. Whereas for the local services, such as network services and so on, are under the same path with /user at the end. So those are the keys for the actual local machine services. So because machine services don't really have credential, the master keys are not actually encrypted with any password. So let's see how these keys are encrypted. So the master keys are encrypted using the LSA secret, okay, which is itself is encrypted using the LSA key. The LSA key is derived by the boot key, which is an encrypted key which is stored in the Windows System Registry Hive, okay? Only the system account is able to read this particular registry key, which means that from an offensive security perspective, if you are targeting machine accounts or running on the host, if you are targeting secrets encrypted with under the context of local services of the host, you will need to compromise the machine. There is no other way around, okay? So let's have a look how we can abuse the DPAPI depending on which context we're targeting. Okay. So for local users, if you're running within the context of the user on the machine itself, on the target itself, we can literally just write a legitimate program which uses the DPAPI legitimately to decrypt encrypted data, because once we run in the context of the user, Windows system will know that we are this particular account, so we will not need to provide the credential, because the credential we already cached on the system itself. So the DPAPI will use the cache credential to decrypt the master keys, derive the symmetric key, and being able to decrypt the data that way. If we actually know the victim password and we have access to the master keys, we can actually grab the master keys, copy over to our own control system, and decrypt the master key offline that way. We don't need to run in the context of the user. If you have compromised the host of the victim, if you obtain local admin or system, we can try to look for unencrypted key material into the local security LSS process. If you're able to gain access to the credit history file of the victim, we can actually grab the file and try to crack the account credential offline. So for the main user is kind of similar, really. So if we obtain access to, in the context of the user on the victim machine, we can still write the software we use the DPAPI legitimately to decrypt the data. If we know the user password or we know the NTLM of the victim, we can grab the keys and decrypt them offline. If we compromise the host, again, we can look for keys into the LSS process. The other main difference is if we are able to compromise the whole Active Directory domain, if you obtain domain admin, for example, you can also export the private key of the domain controller, which means that once you have the private key of the domain controller, you are able to then decrypt all the keys for all the accounts within the network. The other thing important to know is that Microsoft doesn't provide you any way to rotate these keys. So if your domain has been compromised and you suspect someone has stolen your DPAPI keys, Microsoft doesn't give you any way. The only way to fix it is use third-party software, or you have to rebuild the domain from scratch. Internal machine, as I mentioned before, the only way to kind of abuse master key for the DPAPI under the machine context, you need to have compromised the host. So you need to run as a local admin or system privilege in order to grab these LSA, the DPAPI secret from a registry to then decrypt, as well as looking for clear text unencrypted master keys material into the LSS process. There are a lot of different tools to kind of abuse the DPAPI in Windows land. Sharpie DPAPI is probably the most common one, is a .NET software. Mimikatz is another famous one. Mimikatz allows you easily to kind of craft. We talk about how to craft DPAPI at the end of this talk, and also allow you to kind of find unencrypted key material into the LSS process memory. In Packet, if you're running in Python or Linux, in Packet allows you to kind of achieve most of the same functionality as these other tools running from Linux land. And there are a lot of other tools. Those are kind of the really most common ones. So let's have a brief look at a couple of actual practical scenario, right? So let's pretend we have compromised a victim host. We are running in the context of the user. We know the user password. We can use a tool like Sharpie DPAPI, as I mentioned. We pass the master key parameter. We pass the password of the victim in this case. And the second thing highlighted at the bottom, that is the actual unencrypted master key. So that key would allow you to then derive the symmetric key to decrypt the data. So let's pretend that the data in this case is the thing at the top as part of the target parameter, is a blob of base64 encrypted DPAPI data which contain a secret. So we know the master key, we pass this blob of data to the tool again with a bunch of different parameters, and we will be able in this case to decrypt the super secret password stored in this particular encrypted data blob. Other scenarios, so if we actually know the victim password, as I said before, we don't need to run in the context of the victim on the host. We can literally grab the master key material, we can grab the actual encrypted blob we need to decrypt, we copy over to the host, we obtain the master key, and we do the decryption offline. Another thing I mentioned at the start, so the DPAPI allows you to specify an entropy. So when you encrypt data using the DPAPI, you can pass optional parameter entropy. So that's just an array of bytes you can specify. Not all the software use entropy. If they do, this entropy is typically coded within the software itself. So as an attacker, if you're after a particular software, you're trying to decrypt some data encrypted with the DPAPI. If you're having trouble, that usually means that there is an entropy used at the top, and an easy way to get around that is you do some reversing on the software, and you usually are able to easily identify what the entropy is, and then that allows you to then perform the decryption that way. Another thing on Windows, which uses the DPAPI, is Windows credentials. So if you're used to, for example, when you access an OSI RDP or you access a file share, and Windows asks you to save this particular credential, these credentials are actually stored using the DPAPI. Once they are stored, Windows doesn't give you any way to decrypt them using Windows legitimately. But if you use Sharp DPAPI or any other of these tools, you're actually able to decrypt this data very easily. Another interesting one, as I mentioned before, because master keys are actually encrypted with the user credential, if you are trying to obtain the clear text password of the user and you have access to the master key of the victim, you can grab the master keys and you can try to, in this case, you're generating a kind of a hash, okay? So you can use like Hashcat or John or any typical password cracking tool. So you can pass this hash and try to brute force it in order to try obtaining the actual clear text password of the user. If you're operating under domain user or within an Active Directory domain context, if we have compromised the domain, if we obtain domain admin, these tools also allow us to extract the RSA private key from domain controller. So if you're using Sharp DPAPI, you can just pass backup key as a parameter. That file will be just the output file where the key will be stored and the domain controller IP. You can use Mimikatz. So the second command is using Mimikatz. The last one is using Impacket on Python if you're using Linux, for example. So in this case, using Impacket, let's pretend we're under the context of a domain admin. So we've compromised the domain. We know the domain admin password or NTH or whatever. We are able to then extract the private key and perform decryption of other master keys we might have to obtain using this private key. So in this particular example, we use the private key to kind of target these CH6 user master keys. So we pass the user ID, SID, we point to the private key we obtain from the domain controller, and we are able to decrypt the master key for this domain user that way. So now let's jump into more interesting cases, okay? So browsers on Windows use the DPAPI, not all of them, but Chrome-based browser like Microsoft Edge of Google Chrome, they use the DPAPI for encrypting cookies and kind of credential storage data on the host itself. So the actual data is stored using a secret key called state key. Okay, so this state key is used, for example, to encrypt cookie, for example. And the state key is itself encrypted with the DPAPI. Okay, so we'll talk about more into this because, as I mentioned earlier, things actually have changed, especially in browser land compared to a few months ago. The actual browser data, encrypted data, is stored under writable and readable user folder, which is typically C, user, username, app data. So that particular folder is writable and readable by user by default. And that's where the state key is also stored, which is encrypted on disk, okay? So let's pretend the goal in this case is, okay, we know that the victim is, for example, logged into Gmail or whatever you can think of, really, okay? And we want to take over their authenticated session as an attacker. So what would we do, okay? So before the recent changes that happened at the end of July, okay, this is what an attacker would have done, okay? So if you had access to the user host, I would copy over the local state, okay? The local state is the file which is encrypted using the state key. I will copy over the actual cookies which are encrypted with the state key, and I will copy over to my own control host the master key of the user. So let's pretend I have compromised. So let's pretend the user is domain user. Let's pretend I compromised the domain. I have the private key of the domain controller. What I could have done easily is I could have pointed to the folder containing the user master keys, the file of the private key of the domain controller, and the local state file of the victim, okay? So this, using a tool called Clonium, again, you can use a lot of different other tools, but that's just an example. That would have allowed us to decrypt the state key. Once we had the state key, we could then decrypt the cookies. And once we have the cookie, we can just easily import the cookie into our own browser and take over the session of the victim. But another very interesting way to abuse this, very actually an easy way, is rather than importing these cookies manually one by one into your browser, which sometimes can be a pain unless you use some clever extensions, you could have easily copy all the browser data from the victim machine to your own machine, together with the key material, of course. And because we know that the encrypted data using the DPAPI results in a blob, this blob of data contains the master key unique identifier of the master key that we'll use to encrypt this data. So as an attacker, we could have simply crafted a master key which has the same unique identifier of the victim key on our own system. So what that would have happened is we could have used Mimikatz in this case to craft a master key with this unique identifier at the top, copy with this crafted key into the expected location on the file system where Windows expects the master keys to be. And because the browser knows that this data has been encrypted with this particular master key ID, we have crafted our own one. So once we open the browser, we would be able to automatically, the browser would be able to automatically decrypt the cookies, thinking that the master key belongs to you as an attacker. So we could have taken over the session this way without having to importing cookies manually. So that what happened using the story I mentioned at the start. So the way this particular OT network staff in that particular organization, they were accessing this network using a web browser. So the way they had it set up is they have a corporate Active Directory domain and a completely separate Active Directory domain for the OT network. Okay, these two domains didn't have any relationship with each other. But because users, staff that needed to access this OT network, they using a web browser to access it. The only interface exposed to the corporate was this web browser together with 2FA. They were using corporate workstation to access it. So the way we achieved the goal was to compromise the corporate domain, extract the DPAPI private key from the domain controller, understand which user in the organization supposedly were allowed to access this particular secure network. And then once we identify the devices, we copy over their master key data, we copy over the browser material, and we were able to then decrypt the cookies and bypass the requirement for 2FA or anything credential or 2FA or anything you can think of. As I mentioned, things actually changed. So since the end of July of this current year, Chrome, Edge are doing things differently. So they implemented this thing called application-bound encryption. So they are still using the data protection API to encrypt cookies and so on, but as an attacker, it's not anymore as simple as obtaining access as the user, and once you have that access, you are able to decrypt master keys and then the cookies. It doesn't work like that anymore. The reason is, when you install Chrome or Edge nowadays, the software actually creates a COM object or a service which runs with system privileges, okay? So this particular COM process checks that when this COM object is invoked to decrypt cookies, for example, it checks that the process calling it is the actual legitimate browser. So as an attacker, if you try to call this COM interface outside the Chrome or Edge context, you will not be able to obtain access to the decrypted cookie anymore, okay? So from an offensive security perspective is, you would need to either obtain local admin privileges on the host, so that would allow you to kind of bypass. So once you have local admin, you can actually, there are ways to kind of pretend to be Chrome or Edge in this case. But otherwise, nowadays, not many, especially we talk about domain user, not many domain users usually have local administrative privileges on their workstation nowadays. So from an offensive security perspective, this is getting very, very hard. The other way to get around it is if you actually inject some malicious payloads within the actual Chrome process itself. So the Chrome process runs under the user context. But if the system has some decent EDR or antivirus deployed, injected into browser, it typically results in kind of an indication of compromise, which typically, most of the time, kind of generates alerts on the ADR side, which will kind of trigger a SOC team or a blue team to kind of investigate and see what's happening. But that's not the end of it. So there is a new, I think it's still kind of in a draft stage. So Google is working on this thing called device-bound session credential. So the idea is they want to go one step further, okay? So the idea is that authenticated session will not only be tracked using typical cookies, for example. There will be an extra cookie which will be signed using a key that will be generated and stored securely on the host itself. So this key will be actually stored using DPM or the Trusted Platform Module, which means that even if you obtain local administrative privileges on the victim machine, there is no real easy way to extract the private key, okay? And the idea is, as an attacker, you will need to operate under the context of the user within the user browser, which, as I mentioned before, will likely generate a lot of indication of compromise kind of events on the host. So that's, again, this is coming up. My understanding is this is still in draft, but I believe Google is going to deploy a beta release in the end of this year or early next year to kind of try to test this particular implementation. And that kind of sums up, really. We talk about, from a developer perspective, how use it legitimately. We talk about how it works under the hood. We talk about how browser used to use the data protection API, how it was kind of abusable easily in some circumstances. Now things are getting harder. They are implementing, especially browser, are implementing more security measure to kind of stop these particular attacks of session takeover and so on. We talk about things that are likely coming up anytime soon, within a few weeks or months. And I really hope you learn a bit about data protection API, how it works, how it can abuse, and that's the end of my talk. Thanks for listening.
Busted.